Okay, so in section 6.2, we looked at addition and subtraction of rational numbers. And the truth is that addition and subtraction is far more challenging than multiplication and division. Multiplication and division of rational numbers is a lot easier to work with. So we're going to take a look at what it means to do multiplication and division, specifically multiplication first. And then we're going to draw a picture of what it means as well. So if we have a over b and c over d and they're rational numbers that we're multiplying, a over b times c over d, we can multiply a times c on top and b times d on bottom. Now, we may choose to reduce in that process before we actually do all the multiplication that's present there. But because we can push like the numerators together and the denominators together, it's what allows us to do this thing where we cancel along diagonals, right? That's actually what's allowing that, and I'll show you that when we get there. All right, you ready to see a picture of why this works? Okay. As I'm doing this picture, I want you to take some context of what 3/5 and 3/4 might mean, because it'll make more sense if you have context to this diagram. Okay, so imagine that you have 3/5 of a birthday cake left over from an event. You took it to Super Bowl Sunday. There's so much dessert there, nobody ate it. Right? 3/5 of it's left over. Okay, so we're going to draw a picture for 3/5. And it's going to be like a cake. So it's going to be a rectangle. And you're going to split it up into, we're going to split it vertically. So you're going to split it up into 5 vertical pieces that are all even. And the picture may not be perfect, but it at least gives you a pretty decent idea. And that's not half bad. There's my fifths. And if I've got 3/5 of it present, then I'm going to shade in 3 of them. Okay? 3/5 of the cake are left over. Now I want you to imagine you have that 3/5 of a cake and you get it out the next day to share with your sweet mates or whomever, right? And after that point, or at that point, we'll say at that point, you eat 3/4, not of the original cake, because 3/4 of the original cake's not there, but 3/4 of what's left over. So we could take this blue shaded piece and we could divide it into 4 sections, but that would be really confusing if we did it vertically. So we're going to divide it into 4 sections horizontally, just for a different image so that we can work with it. I'm going to go ahead and divide the whole cake, even though we only have the blue parts left over, just for the sake of it looking kind of filled in. So of the 3/5 left, of the blue piece, we're going to eat 3/4. So we've got 4 rows, right? There's 4 rows there, and we're going to eat 3 of them. So this is row 1, this is row 2, and this is row 3. So the only part that remains are these 3 little blue pieces when we're done. You can almost imagine, oh look, I really just had 20 pieces of cake to start with, right? I brought home 12 pieces from the party, and then 9 pieces of them were eaten by my sweet mates. Can you picture that? Okay. So the piece that's got the double shading in it, and in your book, actually what they do sometimes too is that they go ahead and shade in the whole thing here. That's fine. Either way, it's the pieces that are double shaded. It doesn't matter if you shade everything or if you just shade what remains. It doesn't make any difference. But the pieces that are double shaded are 9, and the total number of pieces that we have in the diagram, counted all together, was 20. And that's exactly what happens if you multiply straight across the top here and multiply straight across the bottom. Okay? So multiplication of fractions actually talks about multiplying by a fractional piece of something that's left over. And cake's a really easy picture to draw this with. So this is called a rectangular region. That's how your book presents this particular diagram, rectangular region. And not only that, but if we'd had the 9 and the 20 at the end that we're able to reduce, we would reduce it further. This just doesn't have that feature. Okay, does that make sense? So this is the diagram you're going to be drawing on a couple of your questions. All right, for fractions. Fractions have identities and inverses. Identities and inverses first show up with integers, but they show up again when we enter the rational number system. So the multiplicative identity is the value that we multiply by, and it doesn't change anything. So if I take the number 1 and I multiply by a over b, it doesn't change a over b. So 1, the number 1, is called our multiplicative identity. And it works for fractions just like it works for whole numbers and integers and everything else. So that's what I was referencing when I said it shows up somewhere else first. It shows up actually with whole numbers, not even with integers. It shows up with whole numbers. It's the number you multiply by that leaves things unchanged. And it often feels like, well, why do I care? Well, I care specifically when I get to fractions, because in order to create equal fractions like you did in the previous section, you had to multiply by the same number on top and on bottom, right? That's what you did in order to create something that was an equal fraction or had the same denominator to add them together. You need to multiply by something on top and the bottom. But if you multiply something by, say, 5 over 5, what does 5 over 5 equal? 1. And that's why you can multiply by 5 on top and 5 on bottom, and it's sort of allowed. It's because you're really just multiplying by 1. It's the multiplicative identity property. So you've been using it all the time, you didn't even realize it. Inverses, multiplicative inverses show up for the first time, though, with rational numbers. We do not have multiplicative inverses for whole numbers or for integers. This is new. So multiplicative inverse is a number that we multiply by and we get the answer of 1. So if you have a over b, then b over a is that value. Because when I multiply a over b times b over a, I get 1. That's what it takes to be the multiplicative inverse, is it satisfies that requirement. It's not because it's the flip. I mean, people want to talk about, it is, right? It is the reciprocal. It is, or the flip, I get that. But the reason that is what we want is because when we multiply them together, we get the number 1. All right, there's quite a few more theorems that we're going to take a look at before we do any problems. Sorry, this is very heavy on theorems at the beginning. Theorem 611 talks about some different properties that show up in equations and inequalities, primarily. The first one's called the distributive property of multiplication over addition. So if you have a over b, c over d, e over f, all rational numbers, and you're multiplying a over b through the c over d plus e over f, it works just like it would work with whole numbers and everything else. We just distribute the pieces through. So a over b gets multiplied by c over d, and a over b gets multiplied by e over f. And then we use our properties that we said for multiplication, where we just multiply the two numerators, multiply the two denominators, and so forth. Okay, the multiplication property of equality says again, a over b, c over d, e over f are rational numbers. And they're saying if a over b is equal to c over d, so two of them are equal. They probably look different, but they're equal. And e over f is just anything else, any other kind of number. That I'm allowed to multiply by e over f on both sides, right, to a over b and to c over d, and it leaves them unchanged. We do this when we solve equations that have fractions in them. Like, for example, if you had 2/3 x equals 4/5, the way that you would solve this is that you would multiply by 3/2. Are you with me? So that's where we see it used. And the reason that it works is because their two quantities were equal already. So can you imagine taking two pieces of paper, throw the iPad around, two pieces of paper, mine and yours, and they're sitting there side by side, and they're exactly the same piece of paper, and we double the size of this, and we double size the other one. They're going to look exactly the same when they're done too, right? And doubling the size of something is equivalent to multiplying both sides, or both pieces of paper, by the fraction 2 over 1. That's what we're looking at. So we're just doubling something. Okay? Do you have a question? Okay. So this is where it started at, or at least my example started at. I'm not saying that 2/3 and 5/2 or 4/5 are the same. It's 2/3 times x. It's a variable. Okay. And I don't know what x is. But what we are usually doing at this point is we're trying to figure out what x is. So we want that 2/3 to go away. And if I choose to multiply these two together specifically because they are multiplicative inverses, like we talked on the last slide, I'm going to be left with just x. And then whatever's on the right-hand side would be my solution to that problem. Yeah, I was just showing you a place where we do use it in solving equations specifically. Okay, I think there's a couple more. Inequality. So the multiplication property of inequality says much the same thing as the equality one that we just did. A over B, C over D, E over F, rational numbers. The difference is that they're deciding that A over B is greater than C over D. And that's the same condition on number 1 and number 2. It's still the same ordering. A over B greater than C over D. A over B greater than C over D. The difference is what you're multiplying by. In number 1, you're multiplying by a positive number. So when you multiply by a positive number, everything stays the same. It was a greater than symbol, it's still a greater than symbol. Okay? But in number 2, you're multiplying by a negative number. And when you multiply by a negative number, the direction, it was greater than, of the inequality changes to less than. That's the key difference here. And I'll just give you a real easy example with just whole numbers, because it works for whole numbers as well. It's just easier to see if I use whole numbers. If you know that 2 is less than 3, which you do, right? Then if you multiply by a positive number, say 5, well, 10 is less than 15. No problem. But if you say take that same value, 2 is less than 3, and you multiply by something negative, we'll go with negative 5. Now you have negative 10 and you have negative 15. Well, from the perspective of like a number line, or from the perspective of like debt, negative 10 is a bigger value than negative 15. Right? On a number line, if we're doing 0 here, negative 10's here, negative 15's here. Negative 15 is smaller. So the direction of the inequality changes when we multiply by negatives. And it works for fractions just like it would work for the whole number example. Oh, good. This is the last slide of properties. Theorem 611, last one. Multiplication, property of 0. Maybe our best friend ever. It says that when we multiply by 0, we get 0. It doesn't matter if it's fraction. It doesn't matter if it would have been whole numbers or integers or anything else. If we multiply by 0, we get 0. So generally speaking, we don't multiply by 0 because it just, isn't a productive thing to do for any reason. Okay, so I think we're going to do one example and then we'll pause and we'll do group work, okay, from the last section. All right, so the example that we're going to do is a solving equations perspective. And look, it looks a lot like the example that I wrote up just a moment ago, 3s and 4s and 5s and everything. So it says, though, that we're going to identify the properties as we use them, okay? And then we're going to do our best to sort of identify all the properties that are there. But the reality is that when you solve things, and have in the past, you do them sort of like, well, this makes sense. This would be the next piece that I would do. And you don't really think about the properties that underlie what you're doing. They're there just the same, whether you recognize them or not. And we're going to do our best to try to recognize them. All right, so what we're going to take a look at is we want to get that 3 over 4 away from x. We need x alone. So what would I multiply 3 over 4 by in order to get it to move or go away? 4 over 3. And if I do it to the left, I have to do it to the right. And there are 2 properties that I'm using as I do that. One is the multiplicative inverse property. That's how you chose the 4 over 3. And the second property that you're using right there is the multiplicative property of equality, in the sense that you multiply by the same thing on both sides. That's that equality property. So that's the first step. The first step is 2 properties in one. So now what happens when you multiply 4/3 times 3/4? You get 1. And I'm going to write it out for a moment. You might not necessarily write it out if you were doing the problem, but we're going to for the moment. So when I multiply that out, this is sort of the third piece that's going on here, that's the multiplicative inverse property as well. Right? It says that when I multiply something by its inverse, I get 1. And then on the right-hand side, I would multiply across the top and across the bottom. And that's just the definition of multiplication. There's not really a property there. That's just how multiplication is defined. So we don't have to identify it, although if you wanted to, you could do so. What's 1 times x? It's x. And it might seem like, well, obviously it's x. It's obviously x because there's a property that says so. You just don't think about it. And that property, this is the fourth one we're doing here, is the multiplicative identity property. It says that when we multiply by 1, it leaves values unchanged. So when we multiply x by 1, we still have x. It's quite a few properties. There's really only 3 properties we used. We just used 2 portions of one of the particular properties there. But we used 3 properties, and probably you didn't really think about a single one of them. If I'd just given you the problem in an algebra course and you did it, you wouldn't really think about these pieces that you're doing. I know my daughter who's working through properties like this right now, she didn't think about it this way, right? She's just doing what her teacher told her to do, flip and multiply, flip and multiply. That's what she keeps telling me, right? But this is what's underlying those abilities to do that. All right, so we're going to stop right there.